Okay, Chapter 11, Section 6, Absolute Convergence and the Ratio and the Root Tests. Okay, so absolute convergence is as follows. So given any series, A sub n, we consider the corresponding series of absolute value of A sub n, right? So here we're looking at a series where the individual terms might be positive, might be negative, um, and so we're going to consider this new series where we're taking the absolute value of each individual term, making them all positive, right? So the alternating series, for example, is a case where they change positive, negative, positive, negative, but it doesn't have to be quite that. It could be a series where some of the signs are positive, some of them are negative, and it may not be reliably as consistent as positive, negative, positive, negative. It's just some of them are positive, some of them are negative. So we're allowing A sub n to be of any sign. And so what we're going to do is we're going to consider this new series where we're just taking the absolute value of each one, making them all positive. Right? So this is a new series whose terms are the absolute values of the terms of the original series. Okay, definition one. So a series, A sub n, is called absolutely convergent if the series of absolute values is convergent, right? So therefore it's absolutely convergent. So note that if A sub n is a series with positive terms, then the absolute value of A sub n equals to A sub n, right? So in other words, this is redundant in the case where they're all positive. And so absolute convergence is the same as convergence in this case. Okay, so here's an example. Consider this series. I think we've seen this one before. So negative 1 to the power of n minus 1 is going to guarantee that the terms change positive, negative, with the first term being n to the power of 1. Okay, I think there's a little mistake here. So when n is equal to 1, then we end up with negative 1 to the power of 0, which is going to be 1. That's how we end up with a positive term there. 1 over 1 squared, which is this term here. When n is 2, when n is equal to 2, we end up with negative 1 to the power of, negative 1 to the power of 1. That's 2 minus 1 is 1. So that's how we end up with a minus for the second term. When n is equal to 3, when n equals to 3, we'll end up with 3 minus 1, which is 2. So the third term should be positive, and then the next term is going to be negative. So this is where there's a little mistake here. This should be minus 1/4. Okay, so n equals to 1, 2, 3, 4. When n equals to 4, we end up with 4 minus 1 is 3. Negative 1 to the third power is going to be negative. And so we end up with negative 1 over 16. Okay, so looking at this guy, what we're going to do is consider... Oh, I don't want him in red. Let's get rid of this thing. We're going to consider the sum as n goes from 1 to infinity of the absolute value of negative 1 to the n minus 1 all over n squared, right? So we're going to take the absolute value of each of these things. Therefore, we strip away the negatives whenever we have them, and so this will end up being just 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... And so this is just the sum as n goes from 1 to infinity of 1 over n squared, right? And this converges by the p-series. Converges by p-series with p equal to 2. We've seen this one before. The sum of all these guys will converge by p-series equal to 2. Okay, so this is equal to this. Right? So we have that this is equivalent to this. In fact, let me just copy it over here. N equals from 1 to infinity of the absolute value of -1 to the n minus 1 all over n squared absolute values. This equals this, and this converges. Therefore, we've shown that this is convergent. So a series is called absolutely convergent if the series of its absolute values is convergent, right? So at this point, we've established that the original series is absolutely convergent because when we took its absolute value, we found that it was convergent, right? So now back to the original one that has the plus minus, we've been able to conclude that now this one is absolutely convergent. Right? So rather than deal with this, where the signs oscillate, positive, negative, positive, negative, positive, negative, of course we could have attempted the test for alternating series test, but we're taking a different approach here. Okay, so rather than dealing with the plus minus, we said, hey, consider this other series where we take the absolute values. That series definitely converges. Therefore, we've concluded that the original series we're working with is absolutely convergent. Let's see what the author did. Okay, so it's absolutely convergent because when we take its absolute values, it equals to this guy. Well, again, there's a little mistake here from the author. This should be that this is a plus here and that this is a minus. So plus minus, okay. Yes, so that's exactly what I got. Okay, so let's look at another example. The alternating harmonic series. We worked with this one before as well. And again, I think the signs are off a little bit here, so let's fix this. So when n equals to 1, we end up with -1 to the power of 1 minus 1, which is 0, and therefore it's going to be positive. That's why the first term is positive, 1 over 1. When n equals to 2, we'll get 2 minus 1, which is equal to 1, and therefore the second term is minus, and then plus, and then minus. So this next term is supposed to be a minus. Okay, so the alternating harmonic. Remember, harmonic is that really famous case, just a harmonic series is this one, and goes from 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4, right? Dot, 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 dot. Very famous, and we know this does not converge. Does not converge. This is a very famous sequence for a lot of reasons. One, it appears a lot in lots of different scenarios in the real world, or in lots of your classes. You'll run into cases that are similar to, or are the harmonic or similar to the harmonic. So it's famous for that, and it's also famous because it's that one example that shows that a sequence, that individual terms of this sequence, the sequence, which is the individual terms of the series, is growing towards 0, right? It's converging towards 0, and yet the whole thing does not converge, right? So having the terms of the series converge to 0 is required, but not sufficient to conclude that the series converges, right? It's important, it's necessary for the terms to go to 0, but it's not enough to be able to establish that. Good? Okay, so this guy. So let's go back to the context we're working with. Let's consider this new, n goes from 1 to infinity of the absolute value of -1 to the n minus 1 all over n, right? Well, then that means that this just turns it into exactly the harmonic. This is just going to strip away all the negatives from each of the terms, and we'll end up with 1 plus 1/2 plus 1/3 plus 1/4 plus dot, 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 dot. And this is exactly the harmonic, right? If we strip away all the alternating signs, we're going to get the harmonic. So we're saying that in this case, this sum from 1 to infinity of the absolute value of -1 to the n minus 1 all over n absolute value is equal to the sum from 1 over n and 1 to infinity, which is the harmonic, and it diverges. Harmonic diverges. The sum does not converge to a specific amount. It just grows, keeps growing out of control. Okay, so let's see, is that what the author concluded here? We know that the alternating, okay, again, a little mistake with the author here. So this is going to be a minus again from there, is equal to, we know that the alternating harmonic series, this one, is convergent, but it is not absolutely convergent, because the corresponding series of absolute values is equal to this guy, right? Which is harmonic, or a p-series with p equals to 1, and therefore divergent. Okay, so here we have a case where we know that the alternating harmonic series does converge. We've already established that by the alternating series test. But we've shown that when we take the absolute values in individual terms, it is no longer it's gonna result in something that does not converge. So this is not absolutely convergent. Okay, all right, so let's bring that together. Definitions: a series, A sub n, is called conditionally convergent if it is convergent but not absolutely convergent. So as in example 2 shows, the alternating harmonic series is conditionally convergent, but it is possible for a series to be convergent, but not absolutely convergent. Okay, so there's an example of something that's conditionally convergent. And then this third theorem, this is where it pays off, or why we're studying this. This theorem says that if a series is absolutely convergent, then it is convergent. Okay, so stating absolute convergence is a stronger statement than just saying convergent. It's kind of like saying, wow, this is going to be really ugly. This goes this way and then comes back this way, and there's a little bump for, wow. This is my ugly guess. That's supposed to be Texas. Anyway, here's the U.S., and we got ourselves California somewhere. Wow, that's a really ugly California, but okay, you get the sense. Here's Cali. Okay. So just because someone is an American does not make him a Californian, right? Obviously. But if someone is a Californian, then they are an American, right? So saying that you're a Californian gives you more information, right? You know you're a Californian, then you know you're also an American. But simply saying, here's a person, that person is an American, that doesn't make them a Californian, right? So in the same way, we have that being convergent is this larger thing, convergent. But then inside here, we have something that's a little bit stronger that's called absolute convergent. Absolute convergent. If you're inside here, if you're absolutely convergent, then that means you're convergent, right? It's a more powerful statement. But simply saying, hey, here's a series, it's convergent, that doesn't mean that it's absolutely convergent. And in fact, if you're on the outside of that, there exists things that are out here that are conditionally convergent. Conditionally convergent. Okay, you're conditionally convergent if you are definitely convergent, but not absolutely convergent. And if you're absolutely convergent, then you're definitely convergent. Okay, sort of, kind of. So being absolutely convergent is a stronger statement. It's gives you more information than conditionally convergent. Okay, conditionally convergent, an example of that was the alternating harmonic. That one is conditionally convergent because it's not absolutely convergent. Okay, and then going back to example 1, we showed that it was absolutely convergent, right? Going back to this example up here, we're looking at example number 1, this one. we were wondering, what about this guy? What is it? Is it convergent, not convergent? We go, okay, wait a minute. Look, we can take the absolute values of the terms. The absolute values of the terms are definitely convergent. And so we were able to establish that the original one is then absolutely convergent. I wrote it up here. There it is. So we were able to do this. So we were able to establish that the original one was absolutely convergent. And so now that we've established the relationship, now we can say that absolutely convergent must mean that the original one is just convergent. Right? So the original question of, is this convergent or not convergent? First, we consider the absolute values. That converges. So therefore, this series is absolutely convergent. And we've just established that if you're absolutely convergent, then you're definitely convergent. So that's how that connects. Okay, so here's another example. Determine whether a series is convergent or divergent. Okay, so here's an interesting one. I think maybe it's the first time we've seen something like this. Remember that by default, if they don't tell you anything else, the argument of the cosine function, the argument of the trig functions, is going to be in radians. That's the preferred method of presenting trig functions, unless they specifically say that these are degrees. So don't let that confuse you. This is not 1 degree, 2 degrees, 3 degrees. This is in radians. Okay, so now if we think about our cosine function, in fact, let's look that up. Let me graph that with Desmos. Let's look at the cosine function. Okay, so here's the cosine function, right? And it completes one period. In fact, let's change this. Okay, so here's the cosine function. It starts off at this point here when the input, the argument of the cosine function is 0. Then we get an output of 1. And then it comes down, 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 down. It's going to cross at pi over 2. It reaches the very bottom of its cycle at -1 when pi equals, when the input, the argument equals to pi. Then at 1.5 pi's, it reaches 0 again. And at 2 pi's, it reaches its maximum to complete its cycle, its period, and then it repeats itself, right? Okay, so 2 pi is the end of its cycle, and that's a little bit past 6, right? That's what this is here. So this is in radians. This is not in degrees. If it was in degrees, it would complete one whole cycle in 360 degrees. So this is definitely in radians. Okay, so now let's look at a table value. Table, where we have n, and we have cosine n. Okay, so when n equals to 1, we have cosine of 1. That's going to be that point. Let's put it in red. Done. Okay, so that's going to be this guy right there. And then when n equals to 2, we'll have that guy, and then 3, and then 4, and then 5. Okay, so here's the first 10 values. And so what we notice is that the numerator of our sequence is going to be sometimes positive. So here's some small positive decimal. Sometimes a negative, then negative, negative, then another positive. So it's going to have both positives and negatives, but it's not going to be in a consistent pattern of positive, negative, the way we have with the alternating sequence. Here we have a positive, and then 3 negatives, and then 3 positives, and then 3 negatives, and I suspect it's going to continue on that pattern. Okay, so the the values are going to be sometimes positive, sometimes negative, but always some value within the cosine function. Okay, so let's take a look at that. Okay, so back to our series. Here's the table of values I got from Desmos. And so this guy, if we wanted to expand it, would mean that this is the same thing as 1 squared for the first term, and then cosine of 1, that would be that 0.54, just to kind of give a little sense of what that is. And then the next term, its cosine of 2 is going to be negative, so then it's going to end up being minus 0.42, 0.42, just to approximate it, and then 2 squared. And then the next term is also negative, so minus 0.98 all over 3 squared. And then the next term, oh, this is a mistake here. 1, 2, this should be a 3 here. It should be cosine of 3, and then cosine of 4. Cosine of 4 is also negative, so minus negative 0.65 over 4 squared. And then the next one is finally positive, so then we have 5 squared in the denominator. Cosine of 5 is 0.28, 0.28, and so on and so forth, so on and so forth, right? So some of them are positive, like this one and this one, but some of them are negative. Whoops, that shouldn't be negative, negative. That should be just be negative. Okay. But some of them are negative, like these three. And so we can see that the signs sometimes are positive, sometimes are negative, and there really isn't a specific pattern that's going to emerge. We have positive, then negative, 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 then positive, 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 negative, 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 positive, 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 and then negative, 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 and then, okay. So there you get a sense of what's happening. Okay, so then tying it back to what we're working with, we're going to say, okay, well then let's consider, in order to answer this question, is this one convergent? Is it divergent? We're going to say, okay, well let's consider this new series that takes the absolute value of each one of these, absolute value of cosine of n divided by n squared. Okay, so now n squared is always positive, especially when you think about the fact that here n is only the counting numbers starting at 1. So n equals 1, 2, 3. Okay, so the denominator is always positive. There's no need to overdo it and say it's the absolute value of something being squared. So we can just rewrite this as n goes from 1 to infinity of the absolute value of cosine of n in absolute values divided by n squared. Okay, so now what we can do is, now that we have this, so this is all positives, right? So this guy, once we apply the absolute value, is going to be each one of these terms except that they're all positives. And we can note that cosine of any value, cosine of x, is always trapped between 1 and negative 1. Right? Therefore, the absolute value of cosine of x, absolute value, is always trapped between 0 and positive 1. More specifically, it's less than 1. Right? So this is where x is any real number. This is for all values, right? All values in the domain of cosine. For x being a member of any real number, this is true. But more specifically, here we have n equals to, for us, n equals to 1 or 2 or 3 or 4, dot, 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 dot. Okay, well, that's just a subset of these. So it's also going to be true, right? So then that must mean that cosine of n in absolute values is definitely less than or equal to 1 or greater than 0, but we don't really need that part. And so we could say that cosine of n divided by n squared, which is a positive number, is less than or equal to 1 over n squared. Right? And we're allowed to do that because we're dividing both sides of the inequality with a positive number. Therefore, the direction of the inequality does not change. Oops, this is in absolute values. Good, 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 good. Okay, so this is a positive. Each term is positive, and we keep adding positive terms. So when we think about the summation, it must be true that the summation must be less than this. So we can say that this sum of cosine n squared as n goes from 1 to infinity must be less than the summation as n goes from 1 to infinity of 1 over n squared. And this one converges by the p-series. With p equal to 2. So this is convergent. Therefore, that must mean that this guy must be convergent, right? So several steps here. So now we must conclude that this guy must converge as well by the comparison test. Converges by the comparison test. Right? Each individual term is positive, so the summation is growing. But we know it's got to be less than or equal to this one, and this one converges by the p-series. Therefore, by the comparison test, we've established that this must converge. Therefore, it must be true that the original one we were working with is absolutely convergent, and therefore it is convergent. Right? So now we've established that the original one we were working with, this series, is absolutely convergent. Absolute. And thus convergent. We've established that it's absolutely convergent, therefore it is convergent. And we've answered our question. Let's see what the author did for this one. The series has both positive and negative terms, but is not alternating. Okay, negatives, 3 positive, okay, irregularly. Okay, so we compare it to that. Cosine of n is less than 1, so we have this is true. We know that this is convergent by the p-series test, so therefore this is absolutely convergent by the comparison test, thus giving us it's absolutely convergent, therefore convergent. Good. Okay, moving on. The ratio tests. So the following test is very useful in determining whether a given series is absolutely convergent. So if we are given a series and we want to establish whether it is convergent or not convergent, we can apply this test. We want to take the n plus 1 divided by nth term in our series, divide them in that order, take their absolute value, and then apply the limit as n goes to infinity. If that limit exists, it equals to L some constant, and that L constant is strictly less than 1. Obviously, because it's absolute values, it can't be negative, so it'll be some decimal between 0 and 1, not including 1. If we can establish that that's true, then we get to conclude that the series we're working with is absolutely convergent and therefore convergent. On the other hand, if the limit as n goes to infinity of the absolute value of n plus 1 over n, a sub n, is equal to some constant that's greater than 1, or if it just grows to infinity, if the limit does not exist and grows off to infinity, then the series is divergent. The only hiccup here is if you do this and you get exactly 1, then this ratio test is inconclusive. That is that there's no conclusion can be drawn about the convergence or divergence. It might converge, it might diverge, right? So you either won't be able to figure it out, or that'll be a clue that you have to try something else because this one isn't giving you the information you need. Okay. Part 3 of the ratio test says that as the limit n goes to infinity equals to 1, the test gives no information. For instance, okay, so for instance, if we think about this one, we've worked with a lot, right? So this is the series of 1 over n squared as n goes from 1 to infinity. N goes from 1 to infinity. If we apply this ratio test, the nth plus 1 term is equal to this one. The nth term is equal to 1 over n squared, right? Just like the 8th term would be equal to 1 over 8 squared. So the nth one is 1 over n squared, and the one right next to it, the n plus 1 term, is going to be 1 over n plus 1 quantity squared. Okay, so if we take this guy, that's this is the a sub n plus 1 term, and divided by the a sub nth term, like this, simplify, numerator times the reciprocal denominator gets you to this guy. They're both being squared, so you can tuck it under one big happy squared power. And then you can do a little bit of algebra to make it look like this. You can also make it look like this by multiplying the numerator and denominator by 1 over n squared. Let's try putting that in here. 1 over n squared gives you a 1 over n squared. Tuck it in there, we end up with 1 over n inside here. Okay, so we get to this, and when we apply the limit, we see that it equals to 1. Okay, and so this is a case where the ratio test leads to us being inconclusive, right? But we already know that this guy is convergent. We've already worked with that. Convergent. And this is because this is a p-series. P-series. With p equal to 2. So we know it converges. It's just pointing out that in this case, the ratio test equaled 1, so we wouldn't be able to reach that conclusion based on the ratio test. We'd have to know it by some other method, which we do. Since we've worked with this one plenty of times before, we know that this is a p-series with p equals to 2. On the other hand, if we look at the harmonic one, right? Remember, again, the harmonic one is this one. Right? N goes from 1 over n equals to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... Okay, and so the nth term out there is going to be plus 1 over n. And the one right next to it would be 1 over n plus 1. Okay, so we take the nth term, that's this guy, divided by 1 over n. Multiplying the numerator times the reciprocal of the denominator gives you this guy. And then again, you multiply the numerator and denominator by 1 over n, multiplied by 1 over n, and we end up with this. And as we apply the limit, we see that it still equals to 1. Again, the ratio test would lead to inconclusive. However, we already know that this is divergent, right? And that's because it's the harmonic series. Harmonic series. Good. Okay, so the point being that this is just highlighting that when the ratio test is applied, if the result is equal to exactly 1, we might get something that is divergent, or we might have something that is convergent. Good. Okay, so when it equals 1, it's inconclusive. You can't conclude one thing or the other. You got to try something else. All right, now let's take a look at this example. Let's do the first few terms here to see what this thing would look like. So when n equals to 1, we end up with 1 to the 1 power divided by 1 factorial plus when n equals to 2, we end up with 2 to the 2nd power divided by 2 factorial plus 3 to the 3rd power over 3 factorial plus 4 to the 4th power divided by 4 factorial, last one, 5 to the 5th power divided by 5 factorial plus ... keep going in that pattern, right? Okay, so then remember, factorial means that we multiply them this way. 1 factorial is just 1. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4. And 5 factorial is 1 times 2 times 3 times 4 times 5. Okay, so you start to see the pattern there. Plus, dot, 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 so on and so forth. And then the numerators, well, we can leave them as powers like this. So that's just going to be 1, and that's 2 squared. I know that's a 4. 3 cubed, that's a 27. 4 to the power of 4, and then 5 to the power of 5, and so on and so forth. Okay, so what we want to do here is consider the ratio test. So the a sub nth term, well, that's just going to be this one. That's going to be n to the power of n all over n factorial. And then, of course, that would mean that the one right next to it, a sub n plus 1, is equal to n plus 1 to the power of n plus 1 divided by n plus 1 factorial. Right? So if we kept going in this sequence here, that's where those two terms would come. Right? Eventually, as we go n equals to 1, n equals to 2, dot, 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 eventually the nth one is out here at n to the power of n divided by n factorial, and the one right next to it would be the n plus 1 to the power of n plus 1 divided by n plus 1 factorial. Okay, so what we want to do is consider the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So that'll be equal to the limit as n approaches infinity of the absolute value of, and then the a sub n plus 1 is this fraction. I'm going to have a little fraction in here, where this is n plus 1 factorial. And this is n plus 1, the power of n plus 1. And then in the denominator, we have n to the power of n divided by n factorial. All of it in absolute values. Okay, so that's going to be equal to the limit as n approaches infinity of, okay, well, n plus 1 factorial, that's going to be a positive term. Positive. There's no negative terms here, right? As you can see here, none of these terms are ever going to turn into a negative. So the absolute value is redundant. We don't need it. So I'm just going to multiply the numerator, that's this fraction, times the reciprocal of the denominator, right? So this fraction times the reciprocal of this one, and then simplify. So I'll end up with n plus 1 to the power of n plus 1 in the exponent divided by n plus 1 factorial times, and then its reciprocal will end up being n factorial over n to the power of n. Okay, so now n plus 1 to the power of n plus 1, we can simplify that a little bit. We can say that that is equal to the limit as n goes to infinity of n plus 1 to the power of 1 times n plus 1 to the power of n. And same thing with this factorial, we can simplify it a little bit. Remember, it's counting up, right? So this, for example, was 5 factorial, 1 times 2 times 3 times 4 times 5. So that means that n plus 1 factorial is a multiplication of 1 times 2 times 3 times 4, dot, 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 times n times n plus 1. That's what n factorial is. Up to there. Times, and then n factorial over n to the power of n. Okay? All right, so that means we can separate this denominator into the part that's just n factorial. That's this part right here. This guy is n factorial times n plus 1. Good. So this will then become the limit as n goes to infinity of n plus 1 times n plus 1 to the power of n divided by n factorial times n plus 1 times n factorial over n to the power of n. So now this will reduce with that, and this will reduce with that, giving me just these two. So I'll end up with the limit as n goes to infinity of n plus 1 to the power of n divided by n to the power of n. And since they both have the same exponent of n, then we can tuck it under one big exponent. So this becomes the limit as n goes to infinity of n plus 1 divided by n to the power of n. And now we can simplify that a little bit and say that that's equal to the limit as n goes to infinity of 1 plus 1 over n to the power of n, right? Distributing this, n over n plus 1 over n gives you this. And this, for some of you, might look familiar. This is exactly equal to e. That's the definition of the number e. Let me show you where that is. It's on page 122 of your book. 222 of your book. Okay, so here we are on page 222 of your textbook. Right down here, there was this introduction of e as a limit. And so there are two popular ways to describe e as a limit. Here's one of them. The limit as x goes to 0 of 1 plus x to the power of 1 over x. And then the other way, which in this case we want to use, is the limit as n goes to infinity of 1 plus 1 over n to the power of n. Right? So this is exactly equal to e. So we had to pull that out. Here's a little table that kind of shows why that's true. If you just put it on an Excel sheet file or something, you can see how this, as x approaches to 0, this will approach the number e. And you can do the same sort of thing with this one. Okay, so this becomes e, and e is approximately 2.718, right? Approximately 2.718, and what matters is that that's bigger than 1, right? So we've established that the limit of, this limit, the limit of a sub n plus 1 over a sub n, is greater than 1. This limit is approximately e. It's equal to e, which is greater than 1. And so we've established that the original sequence that we're looking for diverges by the ratio test. So we can conclude that the original one we're working with diverges by the ratio test. See what the author did on this one. Okay, so a sub n plus 1 over a sub n, same as I got, reduces, bunch of stuff reduces, cancels, gets you to this. Approaches e as n goes to infinity. E is greater than 1, so the given series diverges by the ratio test. Okay, so good, we came to the same conclusion. Note, although the ratio test works for example 5, an easier method is to use the test for divergence, since if we notice, this is always going to be strictly greater than n. Notice that on a term-by-term basis, the first two match, n over n, that's just 1. But in every other case, the numerator is bigger than its corresponding, paired up value in the denominator. So this thing is definitely not going to converge to 0. So that's what matters here, the test for divergence. In order for a series to have a chance to potentially be convergent, it must be true that the individual terms that you're adding up must be getting smaller and smaller and growing towards 0, right? Whereas here, the terms are not getting smaller. That's what this is pointing out. It follows that a sub n does not approach 0 as n goes to infinity. Therefore, the given series is divergent by the test for divergence. Okay. Next, the root tests. The following test is convenient for applying the nth powers. The following test is convenient to apply when the nth powers occur. So the root test indicates that if the limit as n goes to infinity of the nth root of the absolute value of a sub n equals to L, which is strictly less than 1, it's some constant value, it's going to be a positive number, then the series a sub n is absolutely convergent and therefore convergent. If the limit as n goes to infinity of the nth root of a sub n is equal to L, which is strictly greater than 1, or it diverges, then the series is divergent, right? So these are the exact same guidelines as we had for the ratio test. We're just doing the nth root test. Okay, and similar to before, if the limit as n goes to infinity of the nth root of the absolute value of a sub n equals to exactly 1, then the root test is inconclusive, right? So it gives no information. We don't know whether the series is going to converge or diverge. At that point, we would have to try something else, or at the very minimum, the root test is not going to help us out. If you try either the root test or the ratio test, and you get a value of 1, there is no sense in trying the other one, right? You're going to get the same result. So if you try the ratio test and you end up with a limit equals 1, there's no reason to come back and try the root test. And same thing with the root test. If you do the root test and get a 1, then you shouldn't go back and try the ratio test. It's going to be a waste of your time. Inconclusive in one means inconclusive in the other. Okay, so for example, let's look at this one. We have this guy. Test the convergence of this series. Okay, so let's just do the first couple of terms just to see where this is heading, just to see the pattern. So when n equals to 1, we're going to end up with 2 times 1 is 2, plus 3 is 5, so we'll get 5 over 1 times 3 plus 2, that's going to be 5, so 5 over 5 to the power of 1. So that's just going to be 1 to the power of 1, or just 1. Okay, so that was all that just to say it starts off with 1. Plus, now it gets interesting. When n equals to 2, we end up with 4 plus 3 makes it 7, all over 6 plus 2 makes it 8 to the power of 2. Plus, when n equals to 3, we get 6, and 3 makes it 9. And 3 times 3 is 9, plus 2 makes it 11 to the power of 3. Plus, when we get a 4, we get 8 plus 3 is 11. 4 times 3 is 12, plus 2 makes it 14 to the power of 4. And so on and so forth, so on and so forth. Okay, so what we want to do is consider the limit as n goes to infinity of the nth root of the absolute value of a sub n. That's what we want to do. Okay, the absolute values are not necessary. As you can see, all the terms are going to be positive always, so that's kind of redundant. We're going to do the limit as n goes to infinity of, and then we'll have 2n plus 3 all over 3n plus 2 to the power of n, and then we're going to do the nth root of that, which means that these two operations undo each other, and we'll end up with just the limit as n goes to infinity of 2n plus 3 all over 3n plus 2. And so now if we multiply the numerator and denominator by 1 over n, another version of 1, right? This one over this one's another version of 1. And if we distribute it through, we'll end up with the limit as n goes to infinity of 2 plus 3 over n divided by 3 plus 2 over n. And so now as the limit is applied, The limit's applied. As n goes to infinity, this guy's going to go towards 0. This guy's going to go towards 0. So the limit as n goes to infinity of this whole thing is going to be equal to 2/3. Because that is a value that's strictly less than 1, then by the root test, we've established that this guy is going to be convergent. Good. So now we can conclude that this guy is convergent by the nth root test. See what the author did. Probably, hopefully matches. Okay, the nth root gives you that, 2/3, less than 1. The given series is absolutely convergent and therefore convergent by the root test. Oh, yes, absolutely convergent and therefore convergent by the root test. That's what we should have concluded. Okay, rearrangements. The question of whether a given convergent series is absolutely convergent or conditionally convergent has a bearing on the question of whether infinite sums behave like finite sums. If we rearrange the order of terms in a finite sum, then of course the value of the sum remains unchanged, but this is not always the case for infinite series, right? So what is this saying? This is saying that if, for example, we have just a finite set of numbers being added, 1 plus 2 plus 3 plus 4 plus 5, right? Just 5 numbers. They add up to 15. The sum equals to 15. And no matter how we order them, 5 plus 4 plus 1 plus 2 plus 3, or 3 plus 1 plus 4 plus 5 plus 2, no matter how you rearrange them, they always add up to 15, right? That's true for any finite number of them. But what about an infinite number of them? Many of you might have already seen this special little trick, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 dot, 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 right? So this guy going out to infinity, some people see this in the following way. They think of it as grouping them up, right? So what if we group these guys up, right? That's a 0, and then that's a 0, and then that's a 0, and then that's a 0, right? So so then the whole sum is a sum of zeros, right? They group them up that way, and they think, okay, well that must mean that this is really a 0 plus a 0 plus a 0 plus a 0, dot, 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 dot. So the whole sum must be 0, right? And then here's where the trickery comes in. They think, well, what if we regroup them up in the following way, like skip the first one, and they go, well, let's just group these guys up. This one and this one is a 0, and then this one and this one's a 0, right? So just leave the first one alone, and then group up the other ones. And so now if we group them up this way, then this new summation must be equal to 1 plus 0 plus 0 plus 0 plus 0 dot, 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 dot. And they make this weird conclusion that this equals that. So therefore we have that one, kind of grouping it all up together. They do it in the following way, or I've seen it presented in the following way. That 0 is equal to 0 plus 0 plus 0 plus 0 plus 0, dot, 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 dot. Like, okay, that's true. Okay, and then 0 is really equal to 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot, 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 dot. You're like, yeah, that's true. That's true. I get it. That's true. Okay, and then they go, okay, well, let's regroup them. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. And then that's when they do this clever little regrouping of let's group up these and let's group up these and so on and so forth. So then they jump to, well, this is equal to 1, and then these is going to be plus 0 plus 0 plus 0 plus 0 plus 0, right? And then here's the big conclusion. 0 equals that, which equals this, which equals that, which equals that. Therefore, 0 equals 1, and that's when you're supposed to be mesmerized by the magic of this whole thing. And I don't know. Then they jump to weird conclusions about the origins of the universe and spirits and, I don't know, ghosts, and I don't know what they conclude. But, you know, this is exactly what this is addressing. The problem, the mathematical problem, is that we are not allowed to regroup these up in every single case. Now, sometimes we can, sometimes we can't, but this is a case where we cannot. So this is mathematically invalid because of this regrouping, right? No one said you're allowed to do that in math. So that's why this is silliness, right? I've seen this as like the proof that there is a God, right? We started with nothing and then we have a 1. That's how God created the universe. Started with nothing and created a 1. I don't know what that means, but at any rate, so for us, we want to stick to what we're allowed to do. And so a rearrangement of a finite number of terms is always allowed. You're always going to get the exact same sum. On the other hand, a rearrangement of an infinite sum is only going to give you the same sum in certain conditions, right? So by a rearrangement of an infinite series, a sub n, we mean a series obtained by simply changing the order of the terms. For instance, a rearrangement of a sub n might be a sub 1, a sub 2, and then notice that we skip, and normally we put a sub 3, then a sub 4, but we're just moving around the order and putting the a sub 5th next, then a sub 3, then a sub 4, and then instead of doing a sub 6, we jump over to a sub 15, right? So we're just moving the order around, but we're eventually going to have them all. So it turns out that this series, if the series is absolutely convergent, then the series of the sum absolutely convergent series with a sum of s, then any rearrangement of that series has the same sum. So if we have an infinite sum, an infinite series, an infinite sum, and we know that it's absolutely convergent, and we know that its sum is equal to capital S here, then we can do a complete rearrangement and always get the same result. But not the case if it's not absolutely convergent, right? So as I said before, being absolutely convergent is actually a stronger, more important statement than simply saying convergent. Absolutely convergent is more powerful. It implies this. Okay, so however, any conditionally convergent series can be rearranged to give a different sum. So to illustrate this fact, let's consider the alternating harmonic series. So here we have the alternating harmonic series, 1 minus a half plus a third minus a fourth plus 1/5 minus 1/6, so on and so forth. And we haven't proven this, but it equals to ln of 2. Right? Don't worry about where that came from for our purposes, but we know it converges by the alternating series test, and it converges to ln of 2. Okay, so if we simply multiply both sides of the equal sign by a half, we multiply this 1 by a half, that's how we get a half. 1 times a half is a half. And then multiply this term by a half, we get minus 1/4. So we get that guy. Minus a half, times a half, we get 1/6. And then minus 1/8. And then the next one's going to be 1/10, 1 over 10, and so on and so forth, so on and so forth. Okay, so now if we insert zeros in between them, we get this sequence. So all we have to do is put a 0 in there, and then this term, then a 0, then this one, then a 0, then this one. Right? That's how we get to this guy right here. And so now if we consider the summation of the original one, this guy, plus this guy, if we add up the right-hand side, we have 1 multiple of ln2 plus half a multiple of ln2. That's 1.5 multiples of ln2. So the right sides will add up to this guy. And then on the left-hand side, we're going to add up term by term. So we have the 1 adds up with a 0 to just give you a 1. And then we have a minus 1/2 and a plus 1/2. Those two are going to cancel. This guy and this guy are going to cancel. And then the next term is going to be plus 1/3. That's how we get a plus 1/3 there. Good. So that one's been taken care of. And then the one after that, we have a minus 1/4 and a minus 1/4. Together they give you a minus 1/2. That's how we get this one, minus 1/2. Good. The next ones after that is going to be positive 1/5 and 0, which gives you positive 1/5. Okay, so if you add them up term by term by term, eventually you get to this. And if we pay a close attention to this new series on the left-hand side, we notice that it contains the same terms as it does in step 6. So even though we added this one plus this one, all of these are exactly the same terms that we have here. So we have a 1, 1, and then a minus 1/2. The minus 1/2 is right here. And then a plus 1/3, then a minus 1/4, and then a minus 1/4. So all the same terms that we started with are found right here. They're just out of order. That's what's going to happen. And so therefore, we've established that the left-hand side must be equal to ln of 2, which is silly because we just established that it was equal to 3/2 ln of 2. Right? But the rearrangements on the one negative term occur for each pair of opposite terms. The sum of the series, however, are different. In fact, the Riemann proves that if we have a series that's conditionally convergent series and R is any real number whatsoever, then there is a rearrangement of the series that has a sum equal to R. Okay, so that's a pretty powerful statement. That if we have a conditionally convergent series, such as this one, right, the alternating harmonic series, that you can make it equal to anything you want, any real number, as long as you think of some appropriate way to rearrange the order of these guys. That's what that's saying. Okay, for us, all that really matters is that you can only rearrange the order and get the same valid result, keep the same summation total for the infinite series. You can only do that if it is absolutely convergent. If it is conditionally convergent, then you have to be careful because if you rearrange it, you're going to get a different sum. All right, that's it for this guy. Let's try some of your homework out. Okay, so here are the homework exercises for Chapter 11, Section 6. Let's tackle a couple of these. From 2 to 4, let's go over here. Determine whether the series is absolutely convergent or conditionally convergent. Let's look at number 4, for instance. We have the sum from 1 to infinity of negative 1 to the power of n all over n to the power of 3 plus 1. Determine if it's absolutely convergent or conditionally convergent. Okay, so let me write that one down. Okay, so the sum from 1 to infinity of negative 1 to the power of n all over n to the power of 3 plus 1. Okay, so let's consider this guy. N goes from 1 to infinity of the absolute value of negative 1 to the power of n all over n cubed plus 1. Well, then that, of course, will take care of this. So this is equal to the sum, as n goes from 1 to infinity, of 1 over n cubed plus 1. Right? So the absolute values just eliminate this part. Okay, and now this guy, what we want to do is, first of all, note that the denominator is always going to be something positive, for n goes from 1, 2, 3, 4. Cubing each of the input values is going to keep it positive, plus 1 makes it positive. So each one of these terms is positive. And we can compare it to the following. So n cubed is always going to be less than n cubed plus 1, and this is for n equals to 1 and 2 and 3 and 4 and dot, 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 dot. That's always true. And so if we flip it, 1 over n cubed, and then 1 over n cubed plus 1, then it goes in this direction, right? So if we divide by something that's bigger, you're going to get a fraction that's smaller than this fraction. And then we've noted that these were all positive values, so they're greater than 0. So I'm just going to flip that around and say 0 is less than 1 over n cubed plus 1, less than 1 over n cubed. They're all positive values, so now when we want to add them, n goes from 1 to infinity of 1 over n cubed plus 1. That's going to be less than the sum of n goes from 1 to infinity of 1 over n cubed. And this guy converges by a p-series. P-series with p equal to 3, right? So this converges, so this one must also converge by the comparison test. Right, so we can conclude that by the comparison test, converges. So because we were able to show that this converges by the comparison test, then we can go back to our original, right? And we were able to show that this converges absolutely. So absolutely convergent. Okay, let's take a look at, say, number 6. Now we have negative 1 to the power of n minus 1. So that's going to guarantee that alternating. And then times n over n squared plus 4. Okay, so it's going to be negative 1 to the power of n minus 1 times, and then we have this fraction, n divided by n squared plus 4. This is going to be alternating, right, since it starts with a positive, then a negative, then a positive, then a negative. So let's look at the alternating series test. In order to see if this fits under the alternating series test, we first of all have to show that this must be the little b sub n part. Right? So this part is positive, and then this is the part that alternates between positive and negative, positive, negative. So part 1, we have to show that the part that's positive, this part, that it is decreasing. So we need to show that b sub n plus 1 is smaller than b sub n, right? Decreasing. Decreasing. And so to do that, we want to say consider the continuous function f of x, which is equal to x over x squared plus 4. In this continuous case, this is where x is any real number. In this continuous case, it just so happens that if we input the counting numbers of n, we get n over n squared plus 4, right? So in other words, if this is a continuous function, then these values are little dots within there, right? They're a specific subset of these results. So if we can show that this function is decreasing, then we've established that this one is also decreasing. To show that this one's decreasing, we're going to take a derivative. So f prime of x is equal to d dx of x over x squared plus 4, which then, of course, is going to give me the quotient rule. So low d high minus high d low over the denominator, squared we go. Good. So that's going to give me that this is going to be equal to x to the second power plus 4 minus 2x squared, which then gives me 4 minus x squared. Oh, sorry. all over x squared plus 4 squared. Remember, our goal is simply to figure out for what values of x is this negative. Well, the denominator is always positive, right? No matter what you do, no matter what the input value, it's always going to be positive. So when is this thing negative? Whenever the numerator is negative, the whole derivative is going to be negative. So we would say that x squared plus 4 minus 2x squared is negative. It's less than 0 for what values? So x squared minus 2x squared, that's going to be minus x squared plus 4 less than 0, which means that we have 4 minus x squared is less than 0, which means that this factors into 2 minus x, 2 plus x is less than 0. So what values of x, for what values of x is this going to be true? So we could come up with these number lines. We have 2 minus x here, and so let's say that this is 0. So for what value of x can I input in here in order to get a 0 for these? Well, that's clearly going to be a 2. So here's positive 2, and that's the 0. Right? If we put a 2 in here, we get a 0. And then if we put any value bigger than that, we end up getting positives. So, like, we end up getting negatives. So if we put in a 3, a 4, a 5, right? 2 minus 3, 2 minus 4, 2 minus 5, we end up getting negatives in that direction. And then if we put in values to the left of the 2, like a 1, or a 0.5, or a 0, or a negative number, we end up getting positives in this direction. Plus, 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 all the way that way, including going into the negatives. Note that if we plug in a negative 2, 2 minus negative 2 becomes positive 4. Okay, so now we come up with a new number line for the x plus 2, 2 plus x. And so here's the 0 again, and then we have a positive 2 there, and the negative 2 there. So if we plug in a negative 2 into here, then this whole thing becomes the new 0. Right? So plugging in a negative 2 into there, that turns into 0. And then if we plug in any numbers to the right of that, we're going to get a positive number. So putting in a 0, putting in a 2, any of those values, we end up with a plus. So we end up getting plus, 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 plus. And then any number to the left of that will be a negative. Negative, 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 negative. Okay, finally, we can consider what happens when we multiply them. So now we have a new number line which will represent the product of the two. Okay, so here is 0. So if I plug in a 0 for x, we end up with 2 times 2. The whole thing is going to be positive. Okay, and then what happens when we plug in a 2? Well, if we plug in a 2 into here, it's going to be a 0. 0 times 4 would still be 0. So we're going to get a 0 here. And if we plug in a negative 2, we'll get a negative 2 there, a negative 2 there. Here becomes a positive 4, but this becomes 0, so the whole thing becomes 0 anyway. Okay, and then all the in-betweens is where we get something interesting. For any value of x that's inside here, we end up with a positive times a positive, which means we end up with positive values in here. And then over here, we end up with a negative times a positive, which becomes a negative. And then over here, we end up with a positive times a negative, which becomes a negative. Okay, and so we see that the function is going to give us a negative value whenever x is greater than 2 or less than negative 2. And then, of course, we are only interested in n values, where n is equal to 1, 2, or 3, or 4, or 5, dot, 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 dot. So we see that for us, we're going to get negative values whenever n is equal to or greater than 3. Okay, so all of this helps us conclude that this sequence is decreasing for n equal to 3 or higher, right? So we've established that b sub n is decreasing for n greater than or equal to 3. Okay, and that's all we want. We're really interested in what happens in the tail end, not the first few finite numbers. We don't care what happens with n equals to 1 or n equals to 2, but at 3 or higher, forever, we've established that it's decreasing. Okay, that's part A, part 1. Part 2 of the alternating series test is to show that the limit as n goes to infinity of b sub n is equal to 0. Right, so then the limit as n goes to infinity of n over n squared plus 4, this one's going to be easy. Okay, we're going to multiply this guy by 1 over n over 1 over n like this, and we'll end up with the limit as n goes to infinity of 1 over n plus 4 over n. And as n goes to infinity, this guy will go to 0. But then this grows toward infinity, gets infinitely large, so the whole thing equals 0. Okay, so we were able to establish both that it is decreasing and that the limit equals to 0. Therefore, by the alternating series test, we've established that this guy converges. Converges by the alternating series test. Okay, but now we want to establish, does it converge absolutely? Is it absolutely convergent? So now in order to establish that, we got to strip away the signs, right? So now let's go over here and say, consider this. Consider the sum as n goes from 1 to infinity of the absolute value of negative 1 to the n minus 1 times n over n squared plus 4. That guy. Okay, so the absolute values are going to get rid of this. This is equal to the sum as n goes from 1 to infinity of n over n squared plus 4. Okay, and if we look at these terms, let's consider, okay, so consider a new sequence. How about a sub n equal to 1 over n? So this is the harmonic one, right? So such that where the sum of 1 over n is the harmonic, n goes from 1 to infinity. Harmonic series, which we know diverges, right? Diverges. Okay, well, the limit comparison test indicates that if we divide these two and find the limit as n goes to infinity, if it equals to some constant greater than 0, then both sequences will be tidally locked, right? They will both be divergent or they will both be convergent. So let's do that. The limit as n goes to infinity of 1 over n divided by n over n squared plus 4 is equal to the limit as n goes to infinity of 1 over n times n squared plus 4 over n, which is equal to the limit as n goes to infinity of n squared plus 4 over n squared, which then equals to the limit as n goes to infinity of 1 plus 4 over n squared, So as n goes to infinity, this will go to 0, and so the whole limit equals 1, which is greater than 0. It's a constant greater than 0. So by the limit comparison test, both series are connected, right? So by the limit comparison test, because the limit as n goes to infinity of a sub n over b sub n equals to 1, which is a constant greater than 0, then it must be true that if a sub n diverges, so will b sub n. Right? That's what the limit comparison tells us. And, well, the opposite is also true, that if this had converged, then we would be able to conclude that this one also converges. But in this case, because we used a sub n equal to 1 over n is the harmonic series, and this one diverged, then we were able to conclude that the one we're interested in diverges. Right? So we can conclude then, by the limit comparison test, that this guy diverges. Diverges by the limit comparison test. So because it diverges, it means that it's not absolutely convergent, but we established that it was convergent by the alternate, we established that it was convergent by the alternating series test. We just established that it wasn't absolutely convergent. So yes, it converges by the by the alternating series test, but when we tried to apply a more strict rule to see if it was absolutely, but fails to be absolutely convergent, right? This is a more strict guideline. It's kind of like we've established someone's an American. Like, okay, someone's an American. But then we tested, well, are they a Californian? And they're like, nope, it fails to be a Californian. You're still convergent, though. You're alternating. By the alternating series test, we've already established that it was convergent. It's just not absolutely convergent. And so, therefore, a series that is convergent but not absolutely convergent is called conditionally convergent. So that's our conclusion for this one. It's conditionally convergent because it does converge under the alternating series test, but it fails to be absolutely convergent because when we strip away the absolute, when we apply the series of absolute values for this sequence, it fails. Okay, now let's try something like number 20, which says use the ratio test to determine whether the series is convergent or divergent. Okay, so at least they're telling us which test to use. So we have n, 2 times n in parentheses factorial divided by n factorial parentheses to the power of 2. And we want to go from n equals to 1 to infinity. Does this converge or diverge? Use the ratio test. Okay, so let me write that one down. Okay, so 2n factorial divided by n factorial squared. Use the ratio test. Okay, so we want to look at this, the limit as n goes to infinity of a sub n plus 1 divided by a sub n in absolute values. Okay, so this is the limit as n goes to infinity of the absolute value of, and then we have this giant fraction where the numerator is going to be this thing with n plus 1, and the denominator is this thing with n. So, okay, so for the denominator, we just basically copy that. So that would be 2n parentheses factorial divided by n factorial to the power of 2, right? And that's all in the denominator. Now in the numerator, it's this thing with power of n plus 1. It's the one right next to it. So this will be n plus 1 parentheses factorial, and then that whole thing is being raised to the power of 2, and then divided by, and up here we end up with 2 times n plus 1, and then that whole thing is being factorial. All of that is inside these absolute values. So we have this fraction divided by this fraction. We know that in order to simplify that, we multiply the numerator times the reciprocal of the denominator. So this will simplify as the limit as n goes to infinity of the numerator, which is going to be 2 parentheses n plus 1 factorial divided by n plus 1 factorial, and then that is itself raised to the power of 2, times, and then the reciprocal of the denominator will be n factorial squared divided by 2n parentheses factorial. Okay, so remember that factorial, if we have like k factorial, means 1 times 2 times 3 times 4, dot, 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 and we don't stop until we get to k. And so the one right after it would be k plus 1 factorial, would be 1 times 2 times 3, dot, 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 and we don't stop until we get to k plus 1, which of course means that the one that came right before it would be k, which means of course the one that came right before that would be k minus 1. So just refreshing your memory on factorials. So what we could say is that k plus 1 factorial is equal to k factorial times k plus 1, for instance. Or you can break it down even more and say that k plus 1 factorial is equal to k minus 1 factorial times the k plus 1, right? Okay, so just reminding you of how we can simplify the factorials. So let's go ahead and do that. So this is going to be equal to the limit as n goes to infinity of this. Oops, this whole thing was inside brackets here, right? So this whole thing is being factorial. So let's go ahead and distribute this. And so I'll end up with 2n plus 2 in parentheses factorial there. And I'm going to go ahead and break this denominator up as well. So this will be n factorial times n plus 1. And that whole thing is getting squared. Times, and then this one I'm going to leave alone, n factorial squared divided by, and let's leave this alone for now. Let's see how that helps. 2n factorial. Okay, so now this can be simplified a little bit more. It goes to infinity. Okay, so this guy, let's just expand this part here, the 2n plus 2 factorial. Okay, so remember that this is a multiplication of 1 times 2 times 3, dot, 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 and we don't stop until we get to 2n plus 2, which means that the one that came right before it would be 2n plus 1, and the one that came right before that would just be 2n. Right? If we wanted to keep going before that, then we'd start subtracting 1 and stuff. Okay, so that means that this part, 1, 2, 3, 4, 5, all the way up to there, can be rewritten as 2n factorial, and then the rest of it. Okay, so that means that this part here, I'm going to rewrite it as 2n factorial times a 2n plus 1 times a 2n plus 2. Okay, and then the 2n factorial, that part is going to cancel with that, so we're happy there. This 2 can distribute, so it'll be, I can simplify it this way. I'll have 2n in parentheses factorial times 2n plus 1 times 2n plus 2 divided by, and then down here, this can be n factorial squared, and then n plus 1 squared times, and then this guy is n factorial squared, and this guy is just going to be 2n parentheses factorial. Okay, now a bunch of stuff can reduce. This guy will reduce with that guy, and this guy will reduce with that guy, and so this is the only thing that survives. And so we get that this is equal to the limit as n goes to infinity of 2n plus 1 times 2n plus 2 divided by, I'm going to go ahead and expand this out as n plus 1 times n plus 1. I could FOIL it and simplify it that way, or another little trick here is that I could multiply the numerator by 1 over n times 1 over n, and 1 over n times 1 over n. Okay, so as long as I introduce a new version of 1, I haven't changed the fractions. And the reason I wrote it this way is because I want to multiply each one of these binomials by one of these and distribute it inside. So this first binomial can be written as 2 plus 1 over n. That's distributing this 1 over n over that first binomial. Times, and then distributing the other 1 over n over the second binomial, we'll end up with 2 plus 2 over n. Doing the same thing in the denominator, we'll end up with 1 plus 1 over n for the first binomial, and 1 plus 1 over n for the second binomial. And now we're ready to apply the limit as n goes to infinity. As n goes to infinity, this will go to 0, this will go towards 0, this will go towards 0, this will go towards 0, and so the whole thing will go toward 2 times 2 all over 1 times 1, or equal to 4. Okay, so that means that after all that work, we've established that this is going to go toward 4, which is greater than 0, greater than 1. So this guy is equal to 4, so we have that the limit as n goes to infinity of the absolute value of a plus 1 over a over n is equal to 4, which is greater than 1. So that means that this diverges. So that means that the sequence of 2n parentheses factorial divided by n factorial parentheses squared as n goes from 1 to infinity diverges by the ratio test. Okay, all right, let's try another one. Okay, so that's fine with those. Let's try one of these. Use the root test. So this one should be fun. About number 28. Okay, so negative 2n divided by n plus 1 to the power of 5n. Okay, so negative 2n over n plus 1 raised to the power of 5n as n goes from 1 to infinity. Let's apply a couple of these, just get the series going to see what we're dealing with. So when n equals to 1, we end up with negative 2 divided by 1 plus 1 is 2. And the whole thing is raised to the power of 5 times 1, which is just going to be 5. That's just going to be negative 1 to the 5th power, or just negative 1. Plus, now when n is 2, we'll end up with negative 4. and 2 plus 1 is 3. Negative 4 divided by 3. Raised to the power of 2 times 5 is 10. Plus, so that'll end up being a positive number because being raised to an even value. Then next, when n is 3, we end up with negative 6 divided by 4. And then the whole thing is being raised to the power of 15. Okay, so on and so forth, so on and so forth, so on and so forth. Okay, so in some cases they're positive terms, in some cases they're negative terms. So the instructions on this problem did say to use the root test, number 28. It says use the root test to determine whether the series is convergent or divergent. Okay, so in order to use the root test, we need to think about this. The limit as n goes to infinity of the nth root of the absolute value, let's put it in green, put it in blue, the absolute value of this thing. So it'll be negative 2, oops, it'll be this thing to the power of 5n, and there's a negative 2n in there, and an n plus 1 there. Okay, well, as we saw up here, sometimes the terms are positive, sometimes they're negative, but if we're going to apply this absolute value right here, this absolute value and this absolute value, then that means that this is equivalent to the limit as n goes to infinity of the fifth root of just 2n over n plus 1, all of it raised to the power of 5n, right? So the thing that oscillates between positives, negatives is this part right here. So the absolute values just got rid of this, that's all, right? That looks kind of ugly here. Let's change this to 2n. This is 2n. Okay, so now that we applied the absolute values, we get this, and now, sorry, mistake. We want the nth root of this, not the fifth root. The nth root of this and the nth root of that. Okay, so now, remembering what this means, if I can remind you, if we have the third root of x, that's the same thing as x to the 1/3 power. And if we have the eighth root of x, that's the same thing as x to the 1/8 power. So if we have the nth root of x, that's the same thing as x to the 1/nth power. Okay, so armed with that, we can say that this is n goes to infinity of 2n over n plus 1 raised to the power of 5n, and then this nth root can be rewritten as this whole thing being raised to the power of 1/n. Okay, all right, one more thing. Let's see. If we wanted to simplify x squared times x to the third, we add the exponents. This becomes x to the fifth power. But if we had x to the second raised to the power of 3, this we multiply and we get x to the sixth. So in this case, if we wanted to simplify them, we multiply the exponents. So our next step would then be to say that this is equal to the limit as n goes to infinity of 2n over n plus 1 raised to the 5n times 1/n. And so now the n's reduce, giving me power of 5. So this becomes the limit as n goes to infinity of 2n quantity to the power of 5 over n plus 1 to the power of 5. Okay, so we can simplify this a little bit. Let's take out that 2 to the power of 5 and stick it out in front. So we have 2 to the power of 5, that's just some constant. ln of n goes to infinity of, and then we have n to the fifth power divided by n plus 1 to the 5th power. So in fact, let's just bring them back together. I shouldn't have pulled them out in the first place, really. Kind of going around in circles a little bit. This is just n over n plus 1 to the power of 5. And now what I could do is come in here and rewrite this. As long as I'm multiplying it by a new version of 1, then I haven't changed it. So that becomes 1 over n, 1 over n. This is multiplying inside the parentheses by a new version of 1. So this becomes 2 to the 5th power, the limit as n goes to infinity, of 1 over 1 plus 1 over n, all of it raised to the power of 5. And because, so note that x to the 5th power, this function is continuous. Then we can interchange the order here. So this then becomes 2 to the 5th power, and this becomes the limit as n goes to infinity. N goes to infinity of 1 over 1 plus 1 over n, the whole thing raised to the 5th power, right? So we can just stick it inside there. Because it's continuous at where it's going, it's going to go toward 1. So it's continuous at 1 in particular, but this one's just continuous everywhere. So then this becomes 0 and then heads to 1. So we end up with 2 to the 5th power times 1, which is just 2 to the 5th power, or 32. Okay, so we've established that. After all that work, we've established that this whole thing right here is equal to 32, which is greater than 1. That's really that really mattered. So the limit as n goes to infinity of the nth root of the absolute value of negative 2n over n plus 1 in parentheses the power of 5n in absolute values. After all that work, we established that this was 32, which is greater than 1. So by the root test, that means that the series we're interested in diverges. So we've established that from 1 to infinity, the series we were interested in, 2n over n plus 1, the 5n power diverges by the root test. Okay. All right, I think that should be enough to get the ball rolling with homework. As usual, let me know if you have trouble with any one of these. Send me an email, and maybe we can meet up and answer your questions.